Welcome back everyone. In this lecture, I will prove the complete reducibility of finite dimensional representations of semisimple Lie algebras. So, this is also called Weyl's theorem. So, here is the statement. So, we start with G be a semisimple Lie algebra and pi being finite dimensional representations of G. So, then what is the Weyl's theorem guarantees that this pi must be completely reducible. So, what is the meaning of that? So, that is this V can be written as direct sum of irreducible representations. So, V1 etc. Vk, where each Vi must be irreducible. So, this is something we have already seen it for SL2 representations. So, now we have developed enough tool to prove for any semisimple Lie algebras. So, let us prove this. So, first we will actually make some reductions and then at the end we will use the action of Casimir element to locate some suitable complementary representation of given representation. So, that is the idea. So, first let us do this reductions. Okay. So, what we will do, so we actually to begin with we assume that V is actually reducible representation. If V is given to be already irreducible, then there is nothing to prove because V is already irreducible. So, there is no so it is already completely reducible. So, because of that we actually assume that V is reducible representation. In particularly it has some proper non-zero sub-representation. So, what is the meaning of complete reducibility? So, given any proper non-zero representation, so it should have complementary representation. So, what is the meaning of that? So, let us start with proper non-zero representation, call it W. So, this is G submodule. So, then what is the meaning of complete reducibility? This W must have complementary representation. So, that means V can be written as W direct sum W dash for some G sub representation W dash of V. So, this is the meaning of complete reducibility. So, this is also one can rewrite in terms of these short exact sequences. So, it is actually convenient for us to write this. So, maybe I will use that notation. So, in terms of the short exact sequences, so we just take this particular short exact sequence which is given by 0 goes to W, W goes to V, V to V mod W to 0. So, look at this particular short exact sequence for given G submodule W. So, then the complete reducibility also means this short exact sequence actually splits. So, one can actually take this as a definition of this short exact sequence being split. So, there are various equivalence versions, let us not get into those things. So, what I mean by this short exact sequence actually splits. So, that means for this W there exists W dash which is complementary G sub representation. So, that means V is equal to W direct sum W dash. So, that is what I mean by this short exact sequence actually splits. So, these maps let us label them. So, this W to V we call it iota and this V to V mod W we call it this quotient map pi. So, this short exact sequence means the image of this each map at each places. Okay. So, for example, image of this iota. So, that must be same as the kernel of this pi. Okay. Not only that, this iota must be injective. So, this iota is injective and this pi is actually surjective. So, all these conditions actually says that this sequence is short exact sequence. So, it is just a language that is used in homological algebra, and for our convenience we just want to use this language. So, now what we want to do, we want to actually reduce our problem to W having codimension 1. So, this is the step 1. So, let me just write it here, step 1. So, we can reduce the problem to W having codimension 1. So, that means the dimension of W dash is actually 1. Okay. So, let us see how one can do this. So, for that what we do, we just take this home space, so which is actually a G module. So, this is a G module that we have already seen. So, now we construct a sub representation of this, call it V. So, what is V? So, this is those elements from this home V comma W, such that when you restrict this element to W, so that must be a scalar multiple. So, this is just a scalar multiple of identity on this W. Okay. So, this is for some A in W. So, we will see in a minute why we are constructing this submodule. Okay. This is not very hard to check, this is indeed sub representation. So, let us check that. So, this V is indeed G submodule of this home V comma W. So, for that purpose, let us start with some x in G and then W in W. So, we need to verify this x dot W, that must be again element of this V. That means, so we have to consider the action of this x dot f on this W and then see how it is actually given. So, this is by definition, recall that x dot f of V is nothing but x dot f of V minus f of x dot V. So, that means this is given to be x dot f of W minus f of x dot W. Now, note that this f is actually when you restrict it to W, so this is scalar. So, let us say that f restricted to W is nothing but A times identity. So, that means this is going to be A times x dot W minus again this W is being submodule, x dot W is again element of W. So, in particularly f of x dot W is given by A times x dot W. So, in particularly we get A times x dot W minus A times x dot W. So, which get cancels and then we get 0. So, that proves that x dot f when you restrict it to W is actually gives us 0. All we wanted some scalar times identity, but we got indeed 0. So, that means V is indeed G submodule. So, now what we will do, we will construct this another sub representation W which is inside V. Okay. So, this is going to be sub representation of V of codimension 1. So, how this is defined? So, W is those f inside V such that when you restrict f to this capital W, that must be 0. So, this is actually your subspace of this V, and again similar computation tells us that this W is also a sub representation. So, it is easy to check, this is a G sub representation of V. Okay. So, since this is defined using the condition that f restricted to W is scalar for V and f restricted to W is 0 for this W. So, that means this W has codimension 1 inside this V. Okay. And it is easy to see that V modulo W will be just isomorphic to this complex numbers that we have told. So, in particularly we have the following exact sequence. So, we have 0 W and then injected inside V, then onto this V modulo W. So, which is actually one dimensional representation, which is the quotient representation. So, that we denoted by C, because any semisimple Lie algebra acts trivially on any one dimensional representation. So, that is we denote it by C. Okay. So, we got this new exact sequence in which we have this W which has codimension 1 inside V, okay, which is very similar to the one that we started with, but somehow we could modify this V and W so that this W becomes codimension 1 inside V. So, now let us say in this situation we know how to solve this problem. So, let us say this sequence actually splits. Okay. So, assume that we know how to do this problem, how to find complementary sub representation of W in V. Okay. So, that means this V can be written as W direct sum W dash. Now, note that since W dash is coming from V, so this W dash must be generated by some F. Okay. So, since this F is actually element of this V, so F restricted to W must be some scalar times identity on W. Now, note that this W dash is complementary space for W. So, that means this A must be non-zero. Now, replace F by this A inverse F. So, that this W dash becomes C times, let us call it F naught, where this F naught restricted to W becomes just identity on W. So, this is what we have right now. Now, note that the F naught that we have actually constructed from this V. Okay. So, this space subspace spanned by this, okay, this is W dash. So, this is actually one dimensional G representation. So, in particularly if I take x and act it on this F naught, so that must be 0 for all x in G. But what is the meaning of this? Let us rewrite this and then see x dot F naught on any V. So, that is given to be x naught F naught of V minus F of x dot F naught of x dot V. So, this is the formula that is actually given. So, the action of G on this any elements of home V comma W is given to be this. In particularly this is being 0 tells us that x dot F naught of V must be equal to F naught of x dot V. So, that means this F naught is an element of this endomorphism of V. So, that commutes with action of the action of G, So, that means this F naught is indeed G module homomorphism, Now, note that this F naught is also satisfies this following property, F naught restricted to W is given to be identity on W. So, now using this information we see that V can be written as W direct sum the kernel of F naught. Okay. So, this is something very easy to check. For example, so given V in V, you can easily check that this V can be written as V minus F naught of V plus F naught of V. So, note that F naught of V must be inside your W, okay, because F naught is coming from home V comma W. Okay. So, this is actually, so F naught is indeed coming from home V comma W. So, in particularly this F naught V is in W. So, now if you look at V minus F naught of V, then if you apply F naught on this, then you can see that this is going to give us F naught of V minus F naught of V. But F naught restricted to W is identity. So, that means this is going to give us F naught of V. So, this is F naught of V minus F naught of V which is 0. So, that means this is inside the kernel of f naught. Now, you can easily see that. So, the intersection of w intersection kernel f naught is 0. So, w intersection kernel f naught is 0. So, that implies this v must be equal to w direct sum kernel of f naught. Since f naught is actually a G module homomorphism, this kernel must be G submodule. So, this way we have actually established very explicit complementary G submodule for this W. Okay. But we have assumed that if you have a exact sequence like this with this W having codimension 1, those kind of exact sequences actually splits. Okay. So, this is how we are reducing this problem to first some short exact sequences that are having like this leftian W having codimension 1. So, we will see that how one can actually deal this case using this what is called Casimir operator. So, for that we actually further reduce the problem to actually W being irreducible. Okay. So, this is the step 2. So, let us go through and then see what we have done. So, we have reduced the problem to the following case. So, what is the case? So, if we have W which is sitting inside V of codimension 1, if this splits then we are done. Okay. So, that is what we have seen. So, now what is our step 2? Our step 2 is actually we will reduce further that this W we can assume to be irreducible by induction on the dimension of W. Okay. So, we can further assume that using the induction, okay, using the induction on dimension W, that W is indeed irreducible. Okay. So, this is the second reduction that we want to do. So, let us assume W is not irreducible and then see how one can actually reduce this problem. Okay. Let us say W dash is actually a proper sub representation of W. So, let us say W dash is actually proper sub representation of W, okay, G sub representation or submodule. Okay. So, then you can see that we have this following exact sequence. So, we have W modulo W dash which is sitting inside V modulo W dash. So, then we can take the quotient. The quotient will be V modulo W dash modulo W dash. So, which is isomorphic to V modulo W, but we have already assumed W is having codimension 1. So, the dimension of this is 1. So, that means, so this is something we can identify with complex numbers, because G acts trivially on that one dimensional body. So, we have the following exact sequence. So, which is W modulo W dash, then V modulo W dash and then C and then 0. Now, note that the dimension of this W modulo W dash, that must be strictly less than the dimension of W. So, in particularly we can assume this short exact sequence splits. So, in particularly we can actually have a complementary sub representation. So, you can write this V modulo W dash is as equal to W modulo W dash direct sum W tilde W dash. So, for some this complementary representation, note that the dimension of this W tilde modulo W dash, that must be 1, and this is a complementary G submodule to this W modulo W dash inside V modulo W dash. So, now we have this information, let us keep this aside. So, now we can use this W dash W tilde and then make another short exact sequence. Okay. So, we have this another short exact sequence which is given by W dash sitting inside W tilde, and then you take the quotient which is actually W tilde modulo W dash, which is one dimensional. So, we denote it by C again. So, this is another short exact sequence. Now, note that the dimension of this W dash, because W dash is assumed to be proper inside W. So, this must be strictly less than the dimension of W. So, that means, so we can assume this short exact sequence actually splits. So, in particularly you can write W tilde as W dash direct sum x, where x is the complementary representation of W dash inside W tilde. Okay. So, note that the dimension of x is 1 and x is a complementary G sub representation of this W dash inside W tilde. So, now what we will do, we will use these informations to cook up actually complementary representation of W. So, how we do that? So, we already have this W tilde which is equal to W dash direct sum x, and we also have this V modulo W dash which is given to be W modulo W dash direct sum this W tilde modulo W dash. So, these informations we have. So, now it is not hard to see. So, V must be actually equal to W direct sum x. So, why this is true? So, this is true because first of all the dimension of V must be equal to dimension W plus dimension x, because dimension x being 1. So, this is true. So, the dimension adds up. So, dimension of V is same as dimension of W plus 1, which is dimension x. And note that if we take any V in capital V, then we can look at V plus this W dash, which is the coset. So, V plus this W dash. So, which is an element inside your V modulo W dash, which is given to be W modulo W dash direct sum W tilde modulo W dash. So, in particularly we can write this V plus W dash as some small w W dash plus some x plus W dash. Now, note that, so this means V minus W minus x or W plus x, this must be inside W dash. So, that implies V must be inside your W, because W dash is subset of W. So, W plus x. Okay. So, that means we have proved that this V must be equal to W plus x. So, now dimension adds up. So, that proves that V must be equal to W direct sum x. And it is also not hard to see that W intersection x must be trivial, and since dimension adds up, again that would imply V must be equal to W direct sum x. So, now this way using induction we have actually exhibited actually complementary submodule for this W. Okay. So, again the base case where the induction begins, where W is being irreducible, we haven't considered. So, this step 2 kind of tells us that we can reduce our problem to the following case. So, this is the step 3. So, what we have done? We have actually reduced our problem to W being irreducible, which is sub representation of V, and the quotient of this V modulo W is actually one dimensional. So, these restrictions that we are making. So, what are the restrictions that we are making? W is irreducible G sub representation of V. So, that is once given, and V modulo W has one dimension. So, these are all assumptions that we are making. So, now we will actually use these informations in order to actually establish very explicit complementary subrepresentation of this W using the Casimir element. Okay. So, denote pi by the representation G to GL of V. So, then we can take this C to be this C pi. So, which is an element of endomorphism of V. We have seen that this C commutes with the action of G. In particularly, C is G module map from V to V. Okay. So, in particularly we can talk about the kernel. So, C is a map from V to V. So, we can talk about the kernel C. So, this must be G sub representation of capital V. So, now let us see how it is related to this W. So, we already have this short exact sequence. So, 0 is sitting inside W, W sitting inside V, V quotient to this C. So, this is the short exact sequence that we have already. Now, since W is sub representation, in particularly C should map W to W, okay, because C actually G module map, W being sub representation implies that C should map W to W. Recall that C is also given to be summation this pi of xi times pi of yi, where I range is from 1 to m. So, this is an element inside this endomorphism of V. If we compute the trace of this C, we already seen that this must be exactly equal to the dimension of G. Okay. So, now you can see that G acts trivially on the quotient. Okay. G acts trivially on this quotient V modulo W, and that would imply immediately that C also acts trivially on this quotient V modulo W. Why? Because C is nothing but just the product pi of xi times pi of yi. All this xi, yi, they are all coming from G. So, that means all this pi of x acts trivially on V modulo W. So, C also acts trivially on V modulo W. So, in particularly if we compute the trace of this C which is induced on this V modulo W, so that must be 0. Okay. So, now if we go back and then look at C, how it acts on this W. Okay. Since W is being irreducible, so C must be given to be some scalar times identity on W. So, now in particularly if you compute the trace of this C restricted to W, so that must be given to be lambda times the dimension of this W. Okay. But note that the trace of C acting on this capital V, that is given to be the dimension of G, and C acting on this V modulo W, that is actually trivial. So, that implies the trace of this C acting on this W must be equal to the trace that acting on this capital V. So, which is the dimension of G. So, this implies that lambda times dimension W must be equal to dimension of G. So, that implies lambda must be equal to dimension G divided by this dimension W, which is positive rational number. Okay. So, from this we conclude that this C acts on this W via this positive rational number. So, actually non-zero scalar. Okay, that is what important for us. So, C acts on W as this dimension G divided by dimension W, which is positive rational number. Okay. So, now we will be able to actually use this information in order to actually get the complementary subspace of this W. In particularly the complementary subspace will be given by the kernel of C. Okay. So, let us recall the properties of C. C is a map from V to V and C maps W to W. Not only that, C actually restricted to W is given by some lambda times identity on W, where this lambda is coming from positive rational number. And C, when you restrict or the induced map on this V modulo W is given to be 0. So, these are all the information that is given. So, now using this, as before, you can see that the kernel of C must be submodule. So, this is G submodule of this capital V such that, so if you take V, then this will be equal to W direct sum this kernel C. Okay. So, this will be the complementary submodule of W. Again the proof is very similar. So, for example, you can replace C by lambda inverse of C, then it actually kind of goes back to the case that we considered already. So, this way we have established actually complementary subspace very explicitly using the Casimir operator C. Okay. So, this is how one actually gets the complete reducibility of this finite dimensional representations of semisimple algebras. So, if you think about it, the step 1 and step 2, so that works for any finite dimensional representations. So, we do not need to actually really restrict to this finite dimensional representations of semisimple algebras. So, in any category of finite dimensional representations of any algebras, so we can see that step 1 and step 2 will work. But when we actually reduce to the step 2, which is of the form 0 W V and then V modulo W, which is having codimension 1. Of course, one of the important property that we have already used that actually the algebra that we are talking about, that is the semisimple algebra that acts trivially on any one dimensional representation. So, that is also somewhat used in the proof. So, if you assume that and then if you go through the proof, you can see that for any finite dimensional representation one can reduce to the following. So, W being irreducible and V modulo W having this dimension 1. So, then basically what we do, once we reduce to this case, then we use this Casimir element which acts on this capital V in order to produce the complementary G sub representation of this V. Okay. So, this is very ingenious proof that works algebraically for this theorem. So, when actually Weyl proved his theorem, he used this Weyl's famous unitary trick which uses this Lie groups ideas, okay, in order to prove his complete reducibility, but later people actually found this algebraic proof. Okay, I will stop here. I will continue with the structure theory of semisimple algebras in the next class. Okay, thanks. Thank you very much.